Chapter 5. And we're going to start looking at different types of functions now, specifically logs and exponential functions. And hopefully you remember from your days in pre-calculus that logs and exponential functions kind of undo one another, and we'll get to some of those relationships shortly. For today, what we want to do is we want to start talking about the properties of the graph. So we want to look specifically at what happens with that graph, what we know about it, how we know it, and then use that hopefully as a visual to help us make some of these other things easier. We're also going to look at properties of logs, and we're going to look at how to differentiate log functions, or specifically natural logs. So natural log function. This is the technical definition, natural log function. So again, thinking back to your days in pre-calc, natural log has a base of E. E is that number about 2.7 something. We'll get to that eventually. But when I look at it, what this really means, this is really the definition of what a log is, or what natural log is. It's the area under the curve, starting at 1 and going to some specific x value of 1 over t dt. And we'll start hopefully to tie that together eventually too. For now, here's a little bit of a review on what we know about the natural log function. Hopefully from your days in pre-calc, you'll recall that every natural log function goes through 2 points. One of those points is the point 1, 0, and it also goes through the point E1. So every natural log function is going to go through the point 1, 0 and the point E1. Why? E is the base of that natural log, so it goes through these 2 points. Every time it's going to go through both of those. It's always increasing, and it's concave down. It has a vertical asymptote at x equals 0, and its domain then, coming straight from there, is anything positive. It can't be negative. And remember your days, you can't take the log of a negative number. Hopefully we'll recall that. And then its range is everything. So as I'm looking at this, what happens with this natural log function, so if E is about 2.7 something, we're going to put a dot at about 2.7181, and then we're going to draw this log function that has a vertical asymptote at x equals 0, so it's going to come up and it's going to do something like that. Is that perfect? No. We just know that it can't cross the y-axis, because it's always going to have, we're going to be using it only for positive x values. So a little quick note there, just as a reminder, can't take the log of a negative. Now, we create that graph in order to create a visual for us, a visual that is going to try to help us figure out what's happening with some of these other types of graphs, and then ultimately a visual that'll help us maybe, oh, I can't take the log of that value, or oh, I know what's happening with that graph. We're trying to create a visual that will hopefully stick in our mind. That's the purpose behind graphing. So as a comparison, when I go to look at problem number 1, well, let's see, natural log of x minus 1. Well, knowing what I know about transformations, this graph would be moved 1 unit to the right, and it's going to look exactly the same. So instead of going through the point 1, 0, it's going to go through the point 2, 0. Instead of going through the point E1, it's going to go through 3.7181. It's going to have a vertical asymptote this time at x equals 1. Going to look something like that. And I guess I didn't do a very good job of drawing my vertical asymptote for my particular log, my original log graph. So there's the only difference. When I look at problem number 2, well, now we notice that this time natural log of absolute value of x. Well, normally we can't take the log of a negative number, but this time the absolute value is going to make every x value eventually positive before we actually put it into the log machine, so to speak. So this time I think what we're looking at, if x's are positive numbers, we're going to have the exact same graph that we had before. So if I go to draw this thing, if x is a positive number, I see the exact same graph. But what happens if x is negative? Well, for example, let's take negative 1. If I take negative 1 and I throw it into this particular function, negative 1, absolute value of negative 1 becomes positive. Natural log of positive 1 would be 0. If I take e, natural log, well, let's see, when e, if I did positive e, I'd get y equals 1. Well, if I do negative e, the absolute value says we're basically doing the same thing. So what we've done is we've created with this absolute value we're going to have a mirror image of this graph across the y-axis. So we're going to go to negative 2.7 something, and we're going to create its mirror image. Now, we still can't have a value when x equals 0. There's still a vertical asymptote here down the middle. We still can't use 0, but we can definitely use all values for that absolute value. So there's your properties of your graph. So we just made 3 of those graphs. Now, how does that help me? Well, when I'm starting to look at some of these properties of logs, back in the good old days, we talked about logs. We talked about what kinds of things we could do with them. Properties of logs. I'm hoping these aren't a big surprise. Natural log of 1, according to those graphs that we have up there, natural log of 1 is going to be 0. Natural log of e is going to be 1. Natural log of a times b, a product, is the same thing as natural log of a being added to natural log of b. Natural log of a to the n, you can write that exponent as a coefficient being multiplied by the log. And natural log of a quotient is the same thing as natural log of a minus natural log of b. So there's your log properties. So now the next 3 problems, 3, 4, and 5 is on the back, are all about what do I do in order to use these log properties. So problem number 1, I see a product. I see 2 things being multiplied, so I'm going to rewrite this. Natural log of z plus natural log of the quantity z plus 1 being squared. And you'll also notice I'm taking some liberties with the types of values that we're plugging in. The assumption I'm making for the problems the rest of the way is that we're using values that fit the domain of this particular function, and we're not trying to take logs of, for example, z would have to be a positive number here in order for us to be able to put it into this equation. So now I also see that coefficient of a 2. I can rewrite that also, natural log of z plus 2 natural log of the quantity z plus 1. So there's my first problem. I've done it. I've gone ahead. I rewrote it. That one's been expanded. Number 4, if I want to do the same thing, well, this time what I see is I've got a quotient, so let's write that as subtraction, natural log of 1 minus natural log of e being squared. Let's see, that square, hopefully we've already recognized that square could be written as a coefficient, so let's move it down there in front. Now, natural log of 1 is the same thing as 0. Natural log of e, according to our properties, is the same thing as 1. So we've got natural log of e being 1. Clean all that up. Negative 2. Moving to the next page. Here we are again. One more problem. This time we're going to reverse it, though. Instead of expanding it, my answer to problem number 5 looks a lot like what I was working on in those previous problems. So this time we're going to go the other way. We're going to try to write it as a single quantity. If I wanted to write this as a single quantity, well, let's see. If I start with this much of it, that's subtraction. So I'm going to deal with the 3 halves last. So I've got natural log of x squared plus 1 divided by x plus 1. I change that subtraction into a single log of division minus natural log of the quantity x minus 1. Well, now here I am with subtraction again. If I've got subtraction again, let's do the same thing. So now it's natural log of the quantity x squared plus 1 over x plus 1 being divided by the quantity x minus 1. Well, let's see. Dividing by a quantity is the same thing as multiplying by its reciprocal. So if we did that, that would attach this x minus 1 to the denominator, 3 halves quantity. Let's see. So natural log of, that would put an x squared plus 1 on the top. I already had an x plus 1 on the bottom. So now if I divide by x minus 1 or multiply by 1 over x minus 1, that would put an x minus 1 in the denominator of what we have here. And we could, of course, multiply out that denominator. If we multiplied out that denominator, I think we would end up with, let's see, well, that 3 halves that's out in front, that 3 halves could be an exponent now. So how about natural log of the quantity x squared plus 1 over x squared minus 1 being raised to the 3 halves power. To the 3 halves power. So there is a single log, and I took care of all my coefficients. I don't want to leave any coefficients in there if I can help it. As a little bit of a shortcut, something for for us to kind of look at. If we look at this, a shorter way to go from this step all the way down to here is to look at our terms. We have, it looks like inside that quantity, we have 3 terms. The first term has a positive sign on it, and that's why the x squared plus 1 can go right straight to the numerator. The second and third terms each have negative signs on them. Well, the shortcut is anybody who's in the numerator, or anybody who has a any term that is positive is going to send that quantity to the top of the log. Any term that's negative is going to send that quantity to the bottom of the log, and that is going to work out that way every time. If you want to skip those first 2 steps that I wrote down, if you just look at your terms, you can simplify the log pretty quickly, and we're going to do that to try to make things a little easier on ourselves. So there's your log properties and properties of your graph.